Now we are going to discuss about electromagnetic waves, the production of the waves, properties of the waves and different electromagnetic waves for different purpose. Before going to that, we should see the introduction about these electromagnetic waves. So what is the introduction about these electromagnetic waves? There are two things. Electric field converting to magnetic field converting to electric field. A time varying magnetic field which can create an amount of electric field. This is nothing but the Faraday's law of electromagnetic induction. They will take one magnet placed near to the coil, and this coil is connected to the galvanometer. Whenever the magnet is approaching towards the coil, then you can sense a small amount of current fields or induced fields are developed in the coil. Then we can sense the change in the position of galvanometer needle. So from this example, we can understand that a time varying magnetic field produces an induced EMF or electric fields within the given material. Converse is also true. That is very, very important. Here, time varying magnetic field producing the electric field. Converse means the electric fields which are time varying will produce the magnetic field or not. This is the checking status. This was already proved in the Faraday's law of electromagnetic induction. The converse proposed and modified by James Maxwell. James Maxwell only modified the statement. A time varying electric field produces a magnetic field. Produces the magnetic field. This we can observe. The accidental observation of this phenomenon was observed by Mr. Oersted, actually, where he placed a magnetic compass box near to the current carrying wire. He observed the deflections of the magnetic compass needle. But here, a time varying electric field which produces the magnetic field. This concept leads to electromagnetic waves. Means a wave which contains the characteristics of electric field and magnetic field and which can travel to the longer distances like electric field line. So this why this is called electromagnetic waves. Mr. James Maxwell, who combined the electric field laws and magnetic field laws, and he proposed 4 different theorems. Those are called electromagnetic equations proposed by James Maxwell. Now we are going to see those equations and their modifications. Okay. Now we will see the Maxwell's equations of electromagnetic waves. Maxwell's electromagnetic waves. Or we can write Maxwell's electromagnetism. Maxwell's electromagnetism. Maxwell, who combined the electric field and magnetic field. So the first equation is surface integral E dot ds is equal to q by epsilon naught. This is nothing but Gauss law in electrostatics. The same thing we can apply to the magnetic field. Surface integral B dot ds is equal to 0. This is also called Gauss law in magnetism or magnetostatics. Third one, line integral E dot dl is equal to d phi b by dt. Fourth one, line integral b dot dl is equal to mu naught ic plus mu naught ie into d phi e by dt. This is Ampere's Maxwell law. This is Faraday's law. If you observe the fourth equation, actually Ampere's circuit law is different. Ampere's circuit law is B is equal to mu naught I by 2 pi r. And we can write line integral b dot dl is equal to mu naught I. So b dot dl is equal to mu naught I should be there. But Maxwell predicted another amount of current. That current is called displacement current, and he added the term which is related to the displacement current to the actual Ampere's law. So that's why it is said to be Ampere's Maxwell's modified law of electromagnetism. So this is the original form of Ampere's law. From this expression we are going to find out this expression for the displacement current. These four equations collectively called as Maxwell's electromagnetic equations. Maxwell's electromagnetic equations. Now we will see what is the concept of this displacement current and their correction. Now we will see displacement current. What is this displacement current? Means current which is displacing from one point to another point. So we will see the clarification. Take a capacitor. Plates are positively charged and the side of the plate is negatively charged. Like this. Backside of the capacitor, outside of the capacitor, just try to collect one point. Around this point, please try to assume the magnetic field. So at this point, we are going to find out the electric field due to the positive charge. And electric field and magnetic field both are perpendicular to each other. That's why we will observe, we can assume a perpendicular loop around this point like this. So along this one, actually it should be a circle. So we will try to draw a circle around the point P. So like this. Around this point, in a perpendicular direction, magnetic field is present. But we can say magnetic field is present over the circumference of the circle. Is present over the circumference of the circle. Actually, what is the Ampere's circuit law? B into 2 pi r is equal to mu naught I. Now we can say the time variable magnetic field B at t is equal to mu naught I by 2 pi r. This 2 pi r is nothing but the perimeter of the circumference of the circle, nothing but the length of a curved path. Now this is the point P, which is just outside of the capacitor plate, and around this point we can assume a magnetic field. Now I try to assume the magnetic field with respect to the positive charge to this point P, like this. and we can observe the pot-shaped dielectric material. Means these are all the Gaussian surfaces which are assumption and which are imaginary. Within this Gaussian surface, if you try to calculate the magnetic field, see the equation, left side of the equation is not changing. Right side of the equation is completely becoming 0. Why? There is no exchange of the charge from positive to negative, because we closed these positives with a dielectric material. Dielectrics won't allow any leakage of the flux from one charge to another charge. So all this dielectric surface acts like a reflector, and again it will go back to the original source, creates the induced EMF. So no flux leakage or no flux exchange between the two oppositely polarized surfaces. That's why we can say the magnetic field is 0. So something is happening. Actually, Ampere Circuit Law is mu naught I by 2 pi r. But the result, when we expanded the Gaussian surface, then the result is coming to 0. Which is the reason? What is the reason behind this? Flux. So how can you understand the flux? Phi E is equal to EA. So what we can understand about E? Q by epsilon naught A into A. So A get cancelled, we will get Q by epsilon naught. Now we are going to find out the rate of change in electric flux with respect to the given equation. So the terms will be like this. So phi E is equal to Q by epsilon naught, differentiating on each side. So differentiating with respect to time on both sides. So the equation will be like this. D phi E by dt is equal to d by dt of q by epsilon naught. So we can write 1 by epsilon naught into dq by dt. 1 by epsilon naught into dq by dt is equal to current equal to d phi E by dt. Therefore, from this equation we can write I is equal to epsilon naught into d phi E by dt. Actually, between the capacitor plates, if flux is exchanged, that causes to the conduction of the current. That's why that current is called IC, conduction current. Conduction current is not dependent upon the flux or E epsilon naught. Means this is a new type of current. Mr. James Maxwell, after analyzing all the experiment, he said this one as displacement current. So the expression will change like this. ID is equal to epsilon naught into d phi E by dt. Conduction current means the current, if the current or the electrons are flowing from one type of charged space to the another type of charged space, means positive to negative terminal, that is said to be conduction current. Current is developed due to the conduction of the charge carriers. What is displacement current? The amount of current which is converting to magnetic field, we can write like this. So therefore, this is the expression of the displacement current. It is displaced by small d. So the Ampere's correction, Ampere's law, B is equal to mu naught I by 2 pi r, and it was corrected with the help of mu naught IC plus mu naught ID. So the expressions will change like this. So the corrections are like this. Corrections to Ampere's Circuit Law. So we know that B into 2 pi r is equal to mu naught I. If you integrate B into dl is equal to mu naught I. This I we can write as IC plus ID is equal to integral B dot dl. Therefore, what is the modified form? B dot dl is equal to mu naught IC plus mu naught ID. Therefore, it is mu naught IC plus mu naught. What is ID? Epsilon naught into d phi E by dt is equal to integral B dot dl. So this is the expression for Ampere's Maxwell law and nothing but the correction of the Ampere's law with the help of displacement current. Now how will we use the displacement current? What is the physical significance of displacement current? If you try to remember the Faraday's law of electromagnetism, what is the Faraday's law of electromagnetism? Time varying magnetic field or magnetic flux can produce electric field. In the beginning of this chapter, we discussed that converse is also true or not, but we can prove the converse also true. How? What is the actual statement of the Faraday's law of electromagnetism? Time varying magnetic field can produce electric field or electric flux. Induced EMF, we can write. Induced EMF. But what is EMF? EMF is nothing but the amount of work done. Amount of work done in moving a charge from P1 to P2, where P refers to position 1 to position 2. That means charge exists, EMF will exist. So if EMF exists, magnetic field also will exist. So what we can write? Time varying magnetic field can produce the EMF. Consequent time varying electric fields can also produce the magnetic fields. So this is a small correction and the proof of contradictions with the help of displacement current. So what we started? We started with the magnetic field to electric field conversion, and we took the EMF as the reference, and the EMF is nothing but the traveling of the charge from P1 to P2. So time varying magnetic field can produce the electric field, as well as time varying electric field can produce the magnetic field. Next, we should discuss about the properties and characteristics of the electromagnetic waves and uses of the different electromagnetic waves. Now we are going to see one problem which is related to the displacement current. The problem's statement is like this. What is an instantaneous displacement current of 1 ampere current in the space between the parallel plate of a microfarad capacitor? Means there is a capacitor which contains parallel plates. We should find out the displacement current of 1 ampere current in the space between the parallel plates of a capacitor. Means in this space the current is 1 ampere. This is a conduction current. And what will be the displacement current for this rate? And its capacitance is 1 microfarad. we know that displacement current is equal to epsilon naught into d phi e by dt. Phi e is electric flux, it is nothing but the E into A. D by dt of E dot A. And this A I am bringing to forward epsilon naught A into d by dt of E. We know that electric field is equal to V by D. Therefore, epsilon naught A into d by dt of V by D. And I am moving the d to the front side. Therefore, ID is equal to, we got epsilon naught A by D into dV by dt. Now we can see what is epsilon naught A by D? Capacitance into dV by dt is equal to ID. Therefore, dV by dt is equal to ID by C. What is the displacement current? 1 ampere. What is the capacitor? 1 microfarad. That means 10 power minus 6 farad. So it will be 10 power 6 volts per second. So potential difference per unit time, we got 10 power 6 volts per second. So that is the instantaneous displacement current of 1 ampere current, which is present in between the space of the parallel plate capacitor of capacitance microfarad. Next we are going to discuss about properties of electromagnetic waves. Electromagnetic waves. First we will see the production of the electromagnetic waves. We know that static electrons can produce the electric fields, accelerating charged particles produces the magnetic fields, but these two fields are not time variant. But how to produce the electromagnetic wave? Neither the moving or not the steady, but which one can produce electromagnetic waves? Let us take a charged particle which is making revolutions around nucleus with some frequency. The frequency of the charged particle is its natural frequency. It tends to align like this. We know that within the space, if the charge is accelerating like this, within the space, electric field will produce. And within the space, electric field is produced. Magnetic field produced within the circumference. Space, electric field. The arrow mark which shows the magnetic field. So what we can understand, within the space electric field is produced, on the circumference of the revolutionary path magnetic field is produced. So what we can understand, electric field and magnetic field both are perpendicular to each other with respect to the given plane. And one more thing, these two will move in the same phase. So the continuous revolution of the charged particle along the circular path, which is similar to the magnetic field, creates the electric field within the spaces given. That means we can say this is the magnetic field component of the given electric field. These two will produce each other respectively while the charged particle is rotating with some frequency. Then electromagnetic waves are combinedly produced, And these electromagnetic waves, according to the given structure, it will travel to the longer distances. This point is very, very important. That means electric field and magnetic field produces each other and travels in same phase. Whenever it travels in the same phase, what we can understand is space produces the electric and the circumference produces the magnetic field. And one more thing we can address here is the best example for the electromagnetic wave is light. Light's speed of light symbol is c. So according to the researches did by the different scientists, speed of light is equal to 1 by under root mu naught epsilon naught. Mu naught, which is in the electric fields, mu naught, which is in the magnetic fields, epsilon naught, which is in the electric fields. That means speed of light is directly or inversely proportional or dependent upon the permeability and permittivity of the different fields, which are nothing but the electric field and magnetic fields. Now, the electromagnetic equations speed of the electromagnetic wave in vacuum is given by like this. And we can write this one as mu epsilon, but mu is equal to mu naught mu r, epsilon is equal to epsilon naught epsilon r. So what is mu? Permeability of the medium. Of the medium. What is epsilon? Permittivity of the medium. Suppose it is mu naught or epsilon naught, it is permeability of the free space, epsilon naught permittivity of the free space. 0 represents the free space, means vacuum, we can say that. So speed of electromagnetic wave depends upon permeability of the medium and permittivity of the medium. This permeability is magnetic permeability, epsilon is electrostatic permittivity. So speed of the electromagnetic wave, which is dependent on mu and E, that's why we can say light is the best example of electromagnetic wave. Now we are going to visualize the concept of propagation of electromagnetic wave. Next, the property is visualization. Electromagnetic wave is a combination of electric wave and magnetic wave, or electric fields and magnetic fields. So how can you visualize this? This is positive x-axis, positive y-axis, positive z-axis. Suppose on y-axis, magnetic wave. Electric wave or electric field is traveling along the positive y-axis. Along z-axis, suppose if magnetic field is propagating along z-axis, the resultant of this E and B is nothing but electromagnetic wave. This electromagnetic wave will travel along x-axis, positive x-axis. We can write the amplitude like this. So what we can understand in the basics of these laws, we have discussed, we have seen that electric field and magnetic field both will have the same amplitude as well as they are in the phase perpendicular to each other to the propagation of the wave, but they will be in the same phase. Keeping this point in mind, if electric field is traveling along the y-axis and magnetic field is traveling along the z-axis, then the propagation of electromagnetic field or electromagnetic wave is along the positive x-axis. This point is very, very important. So in this case, then how will you find out the propagation vectors? If it is the case, we can write Ey is equal to E naught into sine kz minus omega t, and Bz is equal to B naught into sine kz minus omega t. This is the propagation vector of the electric field along positive y-axis. This is the propagation vector of the magnetic field along the z-axis. So if this is the case, E naught and B naught are the amplitudes of the corresponding fields. E naught is amplitude of electric field. Electric field. B naught, amplitude of magnetic field. And we know that K is equal to propagation vector. We can find out K is equal to 2 pi by lambda, where omega is equal to angular frequency. We can write Ck. So this is the expressions which are given, and we can find out C is equal to E naught by B naught, and correspondingly we will get 1 by under root mu naught epsilon naught. This gives approximate value of 3 into 10 power 8 meters per second. Then we will get the speed of light in terms of the meters per second. So this is the propagation of the electromagnetic waves along the directions of the vectors. Next one is pointing vector. What is this pointing vector? If the electromagnetic wave is like this, with respect to amplitudes, the amount of energy which is crossing in unit area of the electromagnetic field, the amount of energy which is crossing in unit surface area of the electromagnetic wave This is the amount of energy which is crossing in unit surface area of the electromagnetic wave, represented by S bar. This S bar is called pointing vector. Means which is pointing the direction of the energy propagation in an electromagnetic field. For S bar there is an equation 1 by mu naught into E bar cross B bar. But we know that E and B are mutually perpendicular to each other. Therefore, S bar is equal to E cross B is equal to EB sin theta, sin 90 is equal to 1. That's why S bar is equal to EB by mu naught. Its SI unit is watt per meter square. Or we can write joule per second per meter square, or joule second minus 1 meter power minus 2. We can write like that also. So this is a small introduction and explanation about the Poynting vector. Now we are going to observe the energy density of the electromagnetic wave. We know that these electric field vector and magnetic field vectors are represented by different equations, where Ey is equal to E naught into sine kz minus omega t, as well as Bz is equal to B naught into sine kx minus omega t. So, in a given small volume, dV, the energy of the electric field is given by E bar is equal to half epsilon naught E square dV within the given value. Then what about the energy of the magnetic field? We know that E naught is equal to B naught by mu. That's why we can write 1 by 2 mu naught into B square dV. This is the energy of the electric field of epsilon naught E square. This is the energy of magnetic field 1 by 2 mu naught into B square dV. Now we are going to find out the energy density of these electromagnetic waves. Now the average energy density of electric field is given by half epsilon naught E square. Average is nothing but 1 by root 2 of the given one. So therefore half epsilon naught into E naught by root 2 whole square. So what we can understand from this expression? E naught square by 2, therefore 1 by 4 into epsilon naught E naught square. This is the average density of the electric field. Then what about the average density of the magnetic field? Of the magnetic field. B square by 2 mu naught. So, B bar is equal to B square by 2 mu naught, where B is equal to B naught by root 2 whole square by 2 mu naught. So, it is B naught by 2 into 2 mu naught, nothing but B naught by 4 mu naught. So, this is a average density of electric field, average density of magnetic field. Suppose if UE is equal to UB, we can find out the total density also. If the amplitudes are same, we can say that UE is equal to UB. If UE is equal to UB, total energy is equal to UE plus UB, that is nothing but 2 UG or 2 UB. So, total energy density is equal to 2 UE for the electric field. So 2 into what is UE? 1 by 4 epsilon naught E naught square. 2. So therefore half epsilon naught E naught square. So total energy density for electric field. Then what is the total energy density for the magnetic field? Total energy density for magnetic fields will be 2 into B naught square by 4 mu naught. 2 and 4 get cancelled 2 times. Therefore, it is B naught square by 2 mu naught. Whether we said UE is equal to UB and E is equal to B, therefore at this condition we can find out the square velocity of the electromagnetic wave, nothing but C is equal to under root mu naught by epsilon naught, because E by B formula we will apply to find out the speed of the electromagnetic wave also. This is the version about the electric energy density for the both fields. Next, intensity. What is intensity? The total energy or total electromagnetic energy which is crossing in unit time perpendicular to the propagation of electromagnetic wave is called intensity of the electromagnetic field. The total energy or unit energy which is crossing the electromagnetic field per unit time. Is called intensity of the electromagnetic field. So we can write the equation of intensity like this. Intensity is equal to average energy by surface area into time. So energy which is crossing electromagnetic field per unit time, and this energy should be perpendicular to the propagation of electromagnetic wave. We can write perpendicular to the, which is perpendicular to the propagation of EM wave. So what is the average energy? Half epsilon E naught square by surface area into time. So we will get a half epsilon naught E naught square into C. Therefore B naught square C by 2 mu naught watt per meter square. This is said to be intensity. The next concept is electromagnetic waves has in the form of radiation also. Sometimes if the radiation falls on any reflecting surface or any transmitted surface, the surface can experience the pressure. So now we are going to discuss about the radiation pressure. Suppose there is a wave of energy U which is traveling with the speed of light c. Then its momentum is equal to P is equal to U by C, where U is energy of the wave, C is equal to speed of the wave. Now P is equal to U by C. What is pressure? Force acting on unit surface area of the body. Here may be a reflector or transmitter. We will go to the discussion also in the last. So pressure is equal to P is equal to F by A. But what is F? dP by dt. So already P is U by C. Therefore, 1 by A into F, that is equal to 1 by A into dP by dt, that is equal to 1 by A into d by dt of U by C. With this expression we can say 1 by C into du by dt by A. So what is this? Energy transferred on per unit surface area in unit time is called du by dt by A. It is represented with Poynting vector, and which is similar to the point vector. Poynting vector definition: energy transferred on unit surface area or falls on the unit surface area in unit time is called Poynting vector. So 1 by mu naught into E cross P. So that's why you can write in this place S. Therefore, pressure is equal to S by C. Momentum is equal to U by C, pressure is equal to S by C. So, momentum is directly proportional to energy, pressure is directly proportional to Poynting vector. If it is a perfect reflector, for reflectors, momentum is proportional to 2U. Therefore, pressure is proportional to 2S. So, therefore, for reflectors, pressure will become 2S by C. Now, we are seeing one problem which is related to the energy densities. The statement is like this. The electromagnetic wave is given by 50 N sine omega of t minus x by C. Find the energy contained in a cylinder of cross section 10 centimeter square and length 50 centimeters along the x-axis. Please, we can write the content. E as given 50 sine omega of t minus x by C. And cross section area A is equal to 10 centimeters square. We can write 10 into 10 power minus 4 meters square. Next one, length 50 centimeters means 50 into 10 power minus 2 meters. Now we should find out the electromagnetic energy contained in a cylinder of cross section. Therefore, electromagnetic energy is equal to half epsilon naught E square into volume. For given volume we are going to find out, but we can write volume is equal to area into length, because in the information we have area and length, we can directly substitute. Therefore, energy we can write half epsilon naught E square into area into length. Now, if the situation is like this, now we are going to substitute half. What is epsilon naught? 8.85 into 10 to the power of minus 12. E, electric field 50. So, 50 square into what is area? 10 into 10 to the power of minus 4 meter square. Length 50 into 10 to the power of minus 2 meters. Meter square into meter, meter cube. So we will get the answer. If you do the same thing, if you do the calculation, we will get approximately 5.5 into 10 to the power of minus 12 joules. This is the electromagnetic energy contained within the given space for this electric field of the lengthy conductors of 10 centimeter square area and 50 centimeters of the length. Now we will discuss about the electromagnetic spectrum. See, this is a diagram which explains the relationship between wavelength and frequency. So wavelength is in the decreasing order, frequency is in the increasing order. We know that C is equal to nu lambda. where lambda is equal to c by nu. That means lambda is inversely proportional to frequency. So wavelength, frequency decreases, wavelength increases. Frequency increases, wavelength decreases. So what is electromagnetic spectrum? It is an array obtained by the arranging of electromagnetic waves on the basis of their wavelengths. It is an array obtained by the arrangement of electromagnetic waves on the basis of their wavelengths. Maybe in the order of increasing wavelengths or decreasing wavelengths, we have arranged all electromagnetic waves. This arrangement is called electromagnetic spectrum. The spectrum contains invisible and visible. What is invisible? This is the visible range of wavelength, 10 power minus 6 meters, and which consists 10 power 15 to 10 to the power of 16 hertz of the frequency. So what we can say before the visible, visible is from violet to red, VIBGYOR, VIBGYOR, VIBGYOR it is. Violet, indigo, blue, green, yellow, orange, red. These 7 colors will contained in the visible. Before visible and after visible are all are invisible. So before visible, what we can expect? Ultraviolet, X-rays, gamma rays. After the visible, infrared, radio and long waves. The whole arrangement from gamma, long waves to gamma or gamma to long waves as the order of increasing or decreasing is called electromagnetic spectrum. In electromagnetic spectrum, this is visible spectrum, all are invisible spectrum. Now we are going to find out or discuss about the production of these waves and their uses. The first one we are going to discuss is radio waves. First, it was discovered by Marconi in 1895. The range of the radio waves is from 500 kilohertz to 1000 megahertz. In these radio waves, amplitude modulation is there, frequency modulation is there. So, what is the amplitude modulation? It is from 530 kilohertz to 1710 kilohertz. The frequencies which lies in between 530 kilohertz to 1710 kilohertz is said to be amplitude modulation. Frequency modulation, FM. So daily we are listening the FM radios. That is under the basis of frequency modulation. The frequency modulation is 88 megahertz to 108 megahertz. In these radio waves, the long wavelengths which are up to 54 kilohertz, are called short wavelengths or short band. These radio waves are used to transmit the TV signals also. So what is the range of TV signals in these radio waves? For TV signals, it is 54 megahertz to 890 megahertz. So this is also 54 megahertz. This is up to short wavelengths. See, this is the original range of radio waves. Among these, amplitude modulation is 530 kilohertz to 1710 kilohertz. Frequency modulation is 88 megahertz to 108 megahertz. In these long wavelengths, up to 54 megahertz is called short wavelengths or short band. From 54 megahertz to 890 megahertz, the frequency range is useful for the transmission of TV signals. So, the cell phone signals are also radio waves, but the cell phone signals will work in ultra high frequency. Nothing but UHF, ultra high frequency. So what is the use of radio waves? It is useful for the TV signals transmission, radio signal transmission, cell phone signal transmission also. Now we will see about the microwaves. It was discovered by Hud, who is the SI unit of frequency, in the year 1888. This frequency range or wavelength range is 10 power minus 4 meters to 1 meter. Wavelength range. This is the wavelength range of microwaves, but the frequency is in gigahertz range. Frequency. To produce these microwaves, we should need a special arrangement like gun diodes, magnetron valves like this. Gun diodes, comma, magnetron valve. These are the instruments. Klystron also. Along with this, klystron. Producers of microwave, this we can say. Once these microwaves are generated by these producers, which can be sensed by semiconductor devices. Sensed by semiconductor devices. Then what is the use of these microwaves? Microwaves are mainly useful for the transmission of radar signals. And these microwaves, which is focused on a particular material for a long time, they can heat up the material's temperature, increases the material's temperature. For this purpose, these microwaves are useful in microwave oven also. Oven, which is useful to bake the food or heat the food. So this is the information about the microwaves. Next we are going to discuss about infrared waves. This was first discovered by Herschel in 1800. Their wavelength region is 7 into 10 to the power of minus 7 meters to 10 to the power of minus 3 meter. This is the wavelength range. Any object which is heated for high temperatures and which is a thermally excited body, if the ions which are in a matter which are thermally excited, they will release the energy in a form of infrared radiation. That means heating effect is the main source to produce the infrared waves. So infrared waves which are emitted by extremely hot bodies. This is very, very important. If any radiation came out of an extremely hot body, if it is a glass prism can absorb the heat. Because of this point, if you want to analyze or to see the analysis of the infrared waves, Instead of glass prism, it is very better to use rock salt prism. Instead of glass. Mainly because of the heating effect of these infrared waves, these waves are useful for doctors in the treatment of therapeutic surgeries. Not only in the medicine, these infrared waves are useful for the military purpose, to observe the activities of the enemy, and to observe the growth of crops. Observe the growth of crops. This is also one of the use. And many electrical devices which we are using in household purpose also contains infrared waves of less intensity. Best example, TV remotes, video recorders, hi-fi system. These are all the uses of infrared waves. So infrared waves are having best heating effect. That's why it is useful in therapeutic surgeries, in case of medicine also. Next we are going to discuss about visible light. Before this visible light, we have studied up to infrared. That up to infrared is from the bottom to top is invisible. So what is visible light? First, it was studied by Newton in 1666. Not in 1966, it is in 1666. The wavelength range of the visible light is 4 into 10 to the power of minus 7 meters to 7 into 10 to the power of minus 7 meters, or 4000 angstroms to 7000 angstroms. In visible light, violet is the shortest wavelength. Shortest wavelength. As well as red color has the longest wavelength. For this purpose only, red color is useful in traffic signals, danger signs, car headlight, backlights, and any motor vehicles backlight is red color. That means red color can travel to the long distances in a given space, so which we can sense a vehicle which is in front of us. So because of this is the best example of the red color. And the sources of the visible light is all glowing bodies. Any body which is glowing, maybe a candle flame, a fluorescent lamp, sodium lamp, filament bulb, tube light, all are the best examples for the sources of the visible light. Why it is called visible light? This is the visible range for human beings. If you see the infrared waves, these are visible to the snakes also, but infrared waves which cannot be observed by the human eye, means human eye not having that much sensitivity or to analyze the high frequencies and high wavelengths. So that is the point. We are restricting our studies up to visible light from violet to red color. The order of the violet to red color is called visible spectrum. Next one is ultraviolet rays. First discovered by Richter in 1801 when he is studying the electron discharge tubes. So ultraviolet rays, they have the wavelength from 10 to the power of minus 9 meters to 4 into 10 to the power of minus 7 meter. This is wavelength range. The major source for the ultraviolet rays is sun rays. Naturally, the radiation which is emitted by the sun, major of its radiation is UV radiation only. But the ozone layer, which is above the height of 40 to 50 kilometers from the Earth's surface, is filtering or completely absorbing or reflecting the ultraviolet rays. But because of the chlorofluorocarbons which are released by the different electronic devices like computers, refrigerators, the CFCs are damaging the ozone layer, and these ultraviolet rays are directly falling onto the earth, and this is directly falling on the skin of the human beings, and human beings are getting skin cancers, melanin effect, tanning of the skin, these type of diseases. So if this is the small information about the ultraviolet rays, what are the ways we can produce the ultraviolet rays artificially or in lab? Through electronic discharge tubes or electric discharge tubes. If these ultraviolet rays falls on the skin of the human beings, which causes to skin cancer, tanning of skin. But what is the main use of these ultraviolet rays? If these ultraviolet rays are passed through the water, which can kill the germs, which causes for the many diseases, killing germs in water or in any liquid, not only water, because we are taking water daily, which is very essential for our life. That's why I am taking this example. And one more example of this ultraviolet rays is the rays which are coming out of the welding. If you observe the welders, they will have a special goggles. They have a special goggles or face masks which are made up of glass window. What is the reason? The radiation which is coming out of the welding process is UV radiation, which has short wavelength, which causes to the damage of the eyes. So which is have a short wavelength and which can produce a narrow beam. Because of this narrow beam structure, this ultraviolet rays are useful in a operation called LASIK. What is this LASIK? Laser assisted in situ keratomyolysis. Which is useful of this operation, which can be done to the eyes, or maybe which is useful to remove the retina like that. And this example is very much useful in ultraviolet rays exception. These gamma rays are useful in many ways. Before this one, we have discussed the use of these things, and one more example of the ultraviolet rays is we can see like this. To find out the forged documents, fingerprints, in forensic laboratory. So now we are watching this forged documents technology, fingerprints technology to reveal the secrets behind the death mysteries and many mysteries. So UV rays are helpful in like that. And UV rays are very much useful to preserve the food. That's why drinking water and food materials, if you see UV treated food materials and UV treated water, which can be stored for a long time. That is the main purpose. And third one, these UV rays are very much useful to find out the internal structure of the molecules and the arrangement of electrons in the shells. Internal structure of molecules and arrangement of electrons in shells. These are the more uses of the ultraviolet rays. These are very, very important for our daily purpose also. Especially in preserving food, we have now the members in the society are addicted to the fast foods and the storage food. If we go to the summer season, everyone is addicted to almost the soft drinks like fruity or thumbs up or 7-Up tins like that. If you see any fruity or any pouch of the liquids like juices, they will have a UV treated coat. If they didn't treat it with the UVs, okay, UV rays, the germs will increasing in that order, and which will be the contamination of the food. Next, we will discuss about the X-rays. Discovered by Ranjan in 1895. Ranjan is the first Nobel laureate in physics. So in 1895, when he is studying the cathode rays, which is coming out of a photosensitive material, and these cathode rays are completely stopped by metal targets which are having high melting point. So cathode rays completely stopped by the metal target. In this way we can produce the X-rays. So the absorption of the cathode rays by a metal target of a high melting point is the main way to produce the X-rays. High melting points. 10 to the power of minus 12 meters to 10 to the power of minus 8 meters wavelength. What is the use of these X-rays? X-rays can able to show the hidden objects inside the body, like fractured bone, second one, hidden bullet, third one, hidden needle, or any other costly material. What is the reason? If these are completely absorbed by the metal targets of high melting point, the cathode rays, what is the reason to observe the hidden parts? Because these rays can penetrate through the photosensitive materials and transparent materials. Penetrates through photosensitive or transparent materials. This is the main uses of the X-rays, and X-rays are also used to find out the crystal structures. Bragg's diffraction, crystal structure also. In case of solid crystals, if you want to see the internal structure of the any crystal, maybe FCC, BCC, SCC, Bragg's law, n lambda is equal to 2d sine theta formula. So in that way we can find out the internal gaps, cracks and difficulties and the defects of the crystal by using the X-ray. Next one, gamma rays. These gamma rays are first discovered by Becquerel and Madame Curie in 1896. Their wavelength range is minus 14 meters to 10 to the power of minus 10 meters. This is the wavelength range of gamma rays. What are the sources to produce the gamma rays? Any natural or artificial radioactive materials. radioactive materials like uranium, thorium, radium, actinium. These are all the radioactive material series. So from this point we can understand one more point is these radioactive materials will participate in nuclear reactions. That's why the radiations which are released in the nuclear reactions are nothing but gamma rays. The radiations which are released or exhausted in nuclear reactions is or are gamma rays. These gamma rays can react with the photosensitive materials. Their main use is useful for the treatment of cancer. These rays are useful in treating the cancer or treatment of cancer. So this is the information about the gamma rays.